Hi everybody, this is Mr. Folly, in a bad color, and welcome to the first podcast of Semester 2, but the third podcast of Chapter 11. Just to remind you, our test is Chapter 10 through 12, and 12 is actually a really interesting chapter. It's one of my favorites. Ooh, as if you can have a favorite chapter. Topics for this one are solubility with pressure, temperature, and polarity. So what are the effects on solubility with different pressures, temperatures, and polarities? Henry's law, which is a new equation for us, so it's just a plug and chug type of thing. Vapor pressure of solution, which is just a plug and chug thing, but we have that rascally mole fraction in there again. Raoult's law, which is the real equation that goes with that, and then bell jar with solution and pure solvent. So this is an odd thing that AP loves to ask about. So let's go ahead and get started. Factors affecting solubility. So this is gases in liquids. Remember, you can have all kinds of different solutions, but gases in, most of the time we're going to assume are solvents or liquids unless told otherwise. If pressure increases, solubility goes up. If temperature increases, solubility goes down. I don't think you'll have to explain this, but the way I rationalize this is if the temperature goes up, the particles are moving faster. And if they're moving faster, remember, less dense things float. So that force of flotation or buoyancy or whatever you want to call it might be enough to overcome some of the interactions and make the gases rise and effervesce. By the way, effervesce is what you call gases coming out of solution. Precipitation is solids coming out of solutions. Effervescence is the other way around. Nature of the reactants, this means polarity, H bonding, van der Waals, which has to do with size, etc. like that. But they always call it the nature of reactants, so it's really your intermolecular attractions. And then Henry's law basically is a law that addresses pressure, which is the next slide. So you can even hold on to that for a second. Solids. As temperature goes up, solubility goes up, but this is a mostly. Gases, the trends are true all of the time. Solids, it's a mostly trend. Not pressure. So pressure has no effect because you're talking about two incompressible states of matter. Solids and liquids are incompressible. So basically pressure tries to compress them, and you can't do it. Nature of reactants, again, nature of reactants is interactions, which would be polarity, van der Waals forces, etc., etc., etc. Here's Henry's law. Good old Hank. Concentration of a gas above is related to the concentration of the gas dissolved. So I've got myself a happy little solution here, and I'm going to make these gas particles, I'm going to show them like they're not dissolved, but realize they actually would be dissolved. So I've got these black solute gas particles, and I've got some of them up above too. Throw a little container on there, right? So it's going to be a lid that's tight-fitting. C is concentration, which we're talking molarity here, equals K, which is a constant for a particular solution, which means it's got to be given. P is the partial pressure of the gaseous solute. So realize it's not the total pressure, it's the partial pressure of the gaseous solute. So that's the way you come up with that. The other one would be probably would be water. Whoops, it doesn't even look like a W, but probably water. Doesn't have to be, but it almost always is. Basically, the higher the pressure, the more soluble it is. And remember, water's pressure can be found on a table. That's always looked up in a book. So looking at some pictures of this, this comes from your book in case this is hard to read. I know sometimes the pictures are hard to read. This would be low pressure. This would be higher pressure. So what happens is you have low pressure, you squeeze it, and notice how here we have 1, 2, 3, 4 ups, and we have 1, 2, 3, 4 downs. That means it's at equilibrium. Then what happens is you squeeze this, you increase the pressure, and notice now I have 2 ups, or 2 effervesces, and 1, 2, 3, 4, 5, 6, 7 downs. 7 dissolves. Okay. And then you reach a new equilibrium, and your new equilibrium would be 1, 2, 3, 4 ups, 1, 2, 3, 4 downs. So you can change the solubility of it, but if you look and counted the ratios of these different things, or the volume, the number of particles per volume, it's going to be less here because the pressure is higher. Showing you it changes. You can make something dissolve more gases by increasing the pressures. Solubility of several solids is a function of temperature. Notice generally they go up. This one goes down. There's more than one that goes down, but Na2SO4 does go down. And the slopes are, cesium sulfate also goes down, but the slopes are also very variable. Notice how the slope is approximately equal to 0, but it is positive, and the slope of KNO3 is huge. And it does change a little bit over time. Solubility of several gases in water. Notice it's always negative slope. Okay, it does change, but it's always negative. And also, the hotter it gets, the solubility levels off. More on vapor pressure. Vapor pressure is the pressure of an evaporated liquid back down on the original liquid. And then you always have to say in a closed container. In a closed container. Boiling is vapor pressure equals atmospheric pressure. Interactions relate to vapor pressure high, increased attraction, so high interactions, such as hydrogen bonding, decrease vapor pressure, so things stay in the condensed liquid state. Man, I had one of my teachers in 3rd grade tell me I had the handwriting of a 3rd grade serial killer. Writing on this thing, man, this handwriting really is scary. So, I apologize for that. And I'll get later. Just kidding, not threatening. Joke, joke, joke. Vapor pressure calculations. This is Raoult's law. This has an awful lot of junk here. PA, this is the pressure of the part equals the pressure total times the mole fraction of A, or your total pressure equals the mole fraction of A times pressure naught of A. This naught means the normal pressure. So this would come from a book or a reference guide of some sort, or given to you in the problem. Mole fraction of B times the vapor pressure. Again, it's P naught, so you're looking at that. Okay, so basically it's a plug and chug thing. If I want to find the pressure of a part, I would multiply the total thing times that. This equation is most useful if you have a non-volatile part. Remember, non-volatile means it doesn't evaporate much at all. So, now Raoult's law has deviations you should familiarize yourself with, and these are horribly long, so please read them and try and put them in your own words. For a positive deviation, the vapor pressure for a given mixture is greater than would be expected. So your P total is too big. Now, why would that happen? Well, that means that attractions have to be less. And why would attractions be less? The intermolecular bonds in the liquid must have been broken when the liquids were mixed. So, for example, ethanol, CCOH, and water, OHO. Obviously, you can have hydrogen bonding here, but this part right here is a big nub of nothing. This big nub of nothing interferes with water having as many hydrogen bonds as it would like. That means the attractions are less than they should be. So there's one hydrogen bond per molecule and a big nub of nothing. Water molecules have two. Basically, it's hydrogen bonds coming out the wazoo. That would be the electron pairs. The ethanol interferes with the water's hydrogen bonds and therefore makes the liquid more volatile. There's positive. The total pressure is too big because attractions are less. And that's, I guess, all you really need to write down. Negative deviation of Raoult's law. Pressure total is, guess what? Too small. And why would that happen? Attractions increase. And that's really hard to make sense of. But sometimes, you know how hydrogen bonding has to be hydrogen directly bonded to an oxygen, and then that increases the polarity? Well, this can happen, I'm looking right here, when molecules where no hydrogen bonding is present are mixed to form a liquid with hydrogen bonds. So if you've had an H-less oxygen, ketone perhaps, dissolved with something with an H, say a CH4, oops, maybe CH4 is probably a bad example, but that H, just because it's a little bit polar, the forces would be greater than they'd be on their own. So you're looking for an H-less oxygen and then a free hydrogen. Okay, so negative deviation of Raoult's law, the total pressure is too small. Why? Because the attractions increase in solution. So that would be the part not evaporated. Here's the AP question thing that's coming up next. I did this in class, and I actually set this up last year before Christmas break. This is unbelievably slow. It takes something like 3 months to be noticeable, and we'll set it up again in class. This thing right here is called a bell jar, and it's meant so that air does not change from one place to another in it. So in figure A, we have water, and we have an aqueous solution. Both the water and the aqueous solution evaporate. The water evaporates lots. The solution evaporates little. Over time, this is going to be gone, and this evaporation is going to be little, but it'll eventually reach equilibrium, and this will be literally gone. Okay, why does this happen? Because the solute is attractive to the water, so water particles stay with the solute even more. Now what happens is, the question often asks what happens to the concentration of the solution. And you go, oh, the concentration of the solution changes clearly, right? Because there's more water. If you have more water, concentration, which remembers brackets, goes which way? You've increased your solvent. It goes down. That's it. A couple of math problems we'll run through quickly. Pentane, vapor pressure 511 torr, and hexane, vapor pressure 150 torr, are mixed together, and the resulting solution has a vapor pressure of 325 torr. What is the mole fraction of pentane? I wish I had a calculator. All right, so I have two different things here. So my P total equals mole fraction, I'm going to call pentane P, times the P naught of P, plus the mole fraction of, what was it? Hexane, H, P naught, H. So I'm going to fill in what I know. The resulting solution has vapor pressure 325 torr. It really doesn't matter what units your pressure are in, because it's all multiplicative for the conversion, so you can leave it wherever you want. So that means I have mole fraction of pentane. P naught of pentane is 511. Plus mole fraction of hexane. Vapor pressure of pentane is 150. You have two variables, so you're mad at yourself. The other thing you do know is that mole fractions are fractions, and the mole fraction of pentane plus the mole fraction of hexane has to equal 1. So that means the mole fraction of pentane equals 1 minus the mole fraction of hexane. So here's how I will substitute it. I'm going to change my color here. 325 equals, I'm substituting mole fraction of pentane for 1 minus mole fraction of hexane. 1 minus mole fraction of hexane times 511 plus the mole fraction of hexane times 150. Again, I don't have a calculator, I'm really sorry, but I'm sure you math people can do that and find the answer. This will tell me the mole fraction of hexane, which was a dumb thing to solve for because it really asked for the mole fraction of pentane, but mole fraction of hexane equals something that I expect you to know. Mole fraction of pentane equals something else I expect you to know. Guess what? This is question number 1 on your pod quiz. Yay! Hopefully you can do that. If not, if that math hurts you, I feel bad for you. Find the vapor pressure of solution made by mixing 35 grams of Na2SO4 with 175 grams of water. Okay, I'm going to get my calculator out now. There's only so much laziness even I can pull off on a Saturday afternoon. Alright, so vapor pressure of solution made by mixing 35 grams of sodium sulfate with 175 grams of water at 25 degrees Celsius. Vapor pressure of water is 23.76 torr at this temperature. So if I want to find the vapor pressure of a solution, I can do P total equals P, equals mole fraction. I'm going to call it salt, I'll call it Na. P naught salt plus mole fraction H2O, P naught H2O. Salts have no vapor pressure. They're solids. They do not evaporate readily, so that one's going to be gone. So my total pressure is going to be lower because it's going to be the mole fraction of my water times the vapor pressure of water. Uh-oh, I have a phone call. Great, I have to go shovel my mom's driveway. But anyway, so now we have, so I need to figure out the mole fraction of these things. So what I'm going to do first is change my color because I hate the red today. 35 grams of Na2SO4 times dividing bar grams of Na2SO4, 1 mole of Na2SO4. Sodium is 22.99 times 2 plus 32.06 is sulfur plus 64 is oxygen. 142 times dividing bar. Oops, nope, that's it. That's all I needed, those moles. And 35 divided by second answer is 0.246 moles. I have 175 grams of water. Basically the same deal. Whoops. 0.01 grams of H2O. 1 mole. 175 divided by 18 is 9.722 moles. So I need to know the mole fraction of water. So the mole fraction of water equals 9.72 over 9.72 plus 0.246. So 9.72 divided by quantity, 9.72 plus 0.246, and quantity, enter, and that is 0.976. So what I'm going to do is take the mole fraction of water, 0.976, times the regular vapor pressure of water, 23.76, and get my answer of 23.18 torr. That's it. Review. Vapor pressure is high for things that don't evaporate and low for things that don't. So again, vapor pressure, we just messed that concept up a lot. Two volatile things need to use the long Raoult's law. Henry says pressure affects the concentration of gases only. That's Henry's law. Blood dissolves gases and delivers them throughout your body. It literally dissolves them. Literally dissolves them. Things have solubility in blood. Gases have solubility in liquids. For example, blood. Expect bloody questions. Sorry if I've offended the British. Bloody means bad things. And lastly, enjoy the weekend.